Hello friends, today we are going to discuss the questions from rotational motion. These questions are from the year 2023. Total questions we are going to discuss are 10, and all these 10 questions are from the mains. And this is the part 1 for the year 2023. So the first question, it states that two identical solid spheres, each of mass 2 kg and radii 10 cm, are fixed at the ends of light rod. The separation between the centers of sphere is 40 cm. The moment of inertia of the system about an axis perpendicular to the rod passing through its middle point is 10 to the minus 3 kg meter square. So we have to find out the moment of inertia of the entire system with respect to the center of the rod. So in this case, we can just draw an approximate figure for that. So suppose this is one sphere, this is the second one, and the centers are connected by a rod. And the total length of this rod is our 40. And the moment of inertia we have to find out through the axis which passes through the center of the rod. So it means from one end, this will be our 20 centimeter, and mass is given to us as 2 kg. Both are having same mass, and radius is also for same. This is about 10 centimeter, and here also radius is about 10 centimeter. Okay. So in this case, first of all, we are going to find out the moment of inertia of the spheres with respect to the centers. Suppose this is O and this is our O prime, and both spheres are same, so we are going to consider only one sphere, and we can just double it for the second sphere. Okay, so we can say that moment of inertia of sphere about its own center. So we can say this as our I sphere with respect to center, and that is our standard formula, which is 2 by 5 mr square. So we simply substitute the values. This comes as 2 by 5, mass is about 2, and radius is 0.1 whole square. So we get that sphere center will be equal to 0.008 kg meter square. And so basically what we did, let me draw the figure for that. So this is the central axis, let us suppose this is our A prime, and we found out the moment of inertia with respect to point O, and the axis, let us suppose is our B prime. Now we are going to use parallel axis theorem, and the distance between which is our d is our L by 2, that is our 20. Therefore, we can say that our parallel axis theorem and this states that moment of inertia about a prime which passes through the center. Okay. And let that be our I, then this I will be equal to moment of inertia of the sphere with respect to its own center plus m and distance between the two axes, md square. And we simply substitute the values. We get this as 0.008 plus this is 2 and it comes as 0.2 whole square. So this gives us that moment of inertia for axis a prime will be equal to 0.088. Now this moment of inertia we found only for one sphere. Okay. Similarly, because the sphere is same, distance is same, mass is same, so we can simply say total moment of inertia let us call this as IT with respect to axis a prime will be equal to double of moment of inertia for a prime. So this comes as 2 times 0.088 and this will be coming as 0.176 kg meter square. It is written in the, so we can decide this is equal to 176 into 10 to the power minus 3. So therefore 176 6. Next question. It states that a ring and a solid sphere rotating about an axis passing through their centers have same radii of gyration. The axis of rotation is perpendicular to the plane of the ring. The ratio of radius of ring to that of the sphere is square root of 2 by x. The value of x is. So in this case, it is with respect to given as radii of gyration, and we can start from there. So we can say a radius of gyration that is our k will be equal to moment of inertia divided by mass m. Now we have two different objects, ring and solid sphere, and so their moment of inertia will be different. Therefore we can say that moment of inertia for ring, let us call this as our IR, is equal to our mass into radius of the ring and its whole square. And next is our sphere. So you can say this is our I of S will be equal to 2 upon 5 m RS whole square. And it says that they are having same radii of gyration. Thus we can write that same radii of gyration. It means K for ring is equal to K for sphere. And we can write this as our square root of moment of inertia for ring divided by mass is equal to moment of inertia for sphere divided by mass. And we substitute. This gives us, for ring is our mrr whole square root is equal to, this is our 2 by 5 mrs whole square and its square root. So this cancels out and square root also goes away. So we get this as our radius for ring whole square is equal to 2 upon 5 radius of sphere whole square. And this we can write radius of ring is equal to radius of sphere and square root of 2 upon 5. And the ratio is given to us as square root of 2 upon x. Therefore, we can say that our radii ratio for ring to our sphere is equal to square root of 2 upon 5. This is also given to us as square root of 2 upon x. So if you make 1:1 comparison, you can say from here that the value of x is equal to 5. So value of x is 5. Next question. It states that the moment of inertia of a semicircular ring about an axis passing through the center and perpendicular to the plane of the ring is mr square upon x, where r is the radius and m is the mass of the semicircular ring. The value of x will be. So in this case, we are given a semicircular ring whose mass is capital M. So you can say that semicircular ring, its mass is given as capital M and its radius is given as capital R. Okay, and we can draw an approximate figure for that. So this is a semicircular ring, and suppose this is the center, which is O, and let us divide or a small portion of it, the mass of which is our dm. And if, okay, so we can say divide semicircle circular ring into small mass, small element of mass dm. And this semicircle is a representation of an angle. That angle is our pi. So from here we can write that since semicircle semicircle spans pi radians, therefore mass per unit angle let us suppose that is our lambda will be equal to total mass divided by total angle. And also we can write that this small element is suppose having an angle of d theta. So you can say a small element subtending an angle d theta. Therefore we can say that our dm will be equal to lambda multiplied by d theta, and this comes as our m upon pi times d theta. So we can find out the moment of inertia of this small element. Therefore we can say that moment of inertia of small element, let us suppose that is our d of I, will be equal to small mass m and moment of inertia its square, radius square. So we substitute our dm and we get that our di will be equal to m by pi, and this comes as d theta multiplied by r square. Now for complete semicircle we are going to integrate from 0 to pi. So we can say for complete semicircle we get our I will be equal to integration 0 to pi d of I. We substitute the d of I, we get I is equal to 0 to pi, and this comes as r square m upon pi d theta, and this is quite easy. We get this will be equal to our mr square, and we are given that the moment of inertia is our mr square upon x. So it means this is equal to mr square upon x. So we can just write it divided by 1. Therefore we get that the value of x is equal to 1. So value of x is 1. Next question. It states that a force of minus k unit vector acts on the origin of a coordinate system. The torque about the point 2 minus 3 is a unit vector plus b j unit vector. The ratio of a by b is x by 2. The value of x is. So in this case, we have given a force is acting at the origin. So let us suppose that there is a force F which is given as P k unit vector, and it acts at origin. And we are given the torque about the point is AI plus BJ. So we are given that torque about point, that point is 2 comma minus 3, and that torque is, let us suppose, is our tau, and this tau is given as our P I unit vector plus B j unit vector. So we can use the general formula for the torque, and we know that the torque about a point R naught torque about a point R naught, we can write it equation as torque is equal to R minus R naught cross F. And here our R unit vector is our position vector of force application, is position vector of force application. It means the point where force is applied, okay, and which is our origin. So this is our origin, and R naught is the point about which the torque is to be found out. Okay, therefore we can say that our R naught will be equal to 2I minus 3j. So we substitute, and force also we know, therefore we can say our torque is equal to 0 minus 2I unit vector 3j unit vector cross, and this is our minus p k unit vector, and we get this will be equal to minus 2I unit vector plus 3j unit vector, and we have this as cross of minus p k unit vector. And we can take this, first of all the cross product will be our I cross k. I cross k is minus of j, so we can say this is our p, or rather we can say minus p, and we have our I cross k that is equal to our minus of j, and that is 2 minus of j, and j cross k is our I, so this comes as plus 3 of I. So if you multiply by one second, oh sorry, yeah, there is this I So this is our minus of 2 minus 2, yeah, 2 minus 3, and this is minus 2 plus minus this, and this is minus of j, and okay, let me find out the cross product. I think I'm missing something, I'm not sure. So we have this as r minus r naught. This looks good. Okay, let me find out, then it is easier to find out. Minus j and k unit vector, this comes as minus 2 3 0, and this will be 0 0 and minus of p, and from here we get that our I unit vector is our 3 times minus of p, and this will be minus of j, and this will be our 0 and 0, and then we have plus of k, and plus of k will be equal to not 0. This is our minus of 2 and minus of p, and for k it will be 0 comma 0. So this comes as minus 3pi, and this will be minus 2pj, and minus p we can take common, so this comes as our 3i plus 2j, and yes, so this looks good now. So this comes as a of I plus b of j. This giving us, I think there is some problem with the sign. Okay, the problem lies here, my mistake. This is our, let me keep this r naught, this is minus and this is plus, so that's why this goes away, and we have r naught. R naught is our 2 plus I, and this is our plus, so this comes plus and this comes as minus. Now it is correct, and here also this will be your minus, and this comes as minus of this, and this will be our 2 will be positive. Now it is correct. We have here plus, and this is plus. Now it's correct. So we get that our A is equal to 3 and B is equal to 2. And the ratio A upon B is equal to 3 by 2, which is our x by 2. This tells that value of x is equal to 3. So value of x is 3. Okay. There was a basic formulation was wrong. Sorry for that. And next question. It states that a solid sphere of mass 500 gram and radius 5 centimeter is rotated about 1 of its diameter with the angular speed of 10 radian per second. If the moment of inertia of the sphere about its tangent is x into 10 to the minus 2 times its angular momentum about its diameter, then the value of x is. So in this case we are given a moment of inertia as well as the angular momentum relationship is given. And the moment of inertia is about its tangent and angular momentum is about its diameter. So both are the standard formulas. So we can just say that moment of inertia of sphere about its tangent and let us call this moment of inertia as I1. Then we have this I1 is equal to 7 upon 5 mr square, and the angular momentum is with respect to its diameter. So we can say the angular momentum about the diameter let us suppose that is our I2. Therefore we can write, sorry, not I2 but L. So we can write our L will be equal to moment of inertia about the diameter and its angular velocity. And with respect to diameter, the moment of inertia we know is about 2 by 5 mr square and omega. So we are given that I1 is our 3x into 10 to the minus 2. Okay. So we are given that I1 is equal to x into 10 to the minus 2 times L. So we can say that 7 upon 5 mr square is equal to x into 10 to the minus 2, and our angular momentum is 2 by 5 mr square times w. Here this mr square and mr square cancel, 5 and 5 goes away. So we are left with that our 7 upon 2 omega is equal to x into 10 to the power minus 2, and angular speed is given as 10. So we can say this comes as 3.5 divided by 10 is equal to x into 10 to the power minus 2. So this can be written as 35 into 10 to the power minus 2 is equal to x into 10 to the power minus 2. So therefore value of x is equal to 35. So value of x will be equal to 35. Next question. It states that a circular plate is rotating in a horizontal plane about an axis, passing through its center and perpendicular to the plate with the angular velocity omega. A person sits at the center having two dumbbells in his hands. When he stretches out his hands, the moment of inertia of the system becomes triple. If E is the initial kinetic energy of the system, then the final kinetic energy will be E upon x. The value of x is. So this is basically based on the conservation of angular momentum. So we are given that the angular velocity is omega, angular velocity is our omega, and initial moment of inertia, let us suppose, is I. Initial moment of inertia is, let us suppose, I, and its kinetic energy is given as, initially is given as E. So kinetic energy initial is our E, and in terms we can write this as our half I omega square. And it says that as it stretches out its hands, it becomes triple. Okay, so we can say the final moment of inertia, will be equal to 3 times I. Okay, and final kinetic energy final is given to us as E upon x. So we are going to use conservation of angular momentum. Conservation of angular momentum, which means L initial will be equal to L final, or we can say our I omega will be equal to I final, and we have this as omega final. Okay, and this final moment of inertia is our IF is equal to 3 times I. Therefore we can write this as 3 times I omega final, and here I and I cancels out, so we get this as that omega final will be equal to omega by 3. So based on this we can easily find out our final kinetic energy. So we can say kinetic energy final will be equal to our half our moment of inertia final and angular final square. So we can write this over half. This comes as 3 times I whole square and omega up 1 second, not whole square, 3 omega upon 3 whole square. So we get energy final will be equal to, this comes as our 1 by 3, and we can write this as 1 by 2 I omega square, and this is nothing but our initial energy. So we can say this is our E upon 3, and we are given that the final energy is E upon x. So this can be written as E upon x, this giving us that the value of x is equal to 3. So value of x is 3. Next question. It states that for a rolling spherical shell, the ratio of rotational kinetic energy and total kinetic energy is x upon 5. The value of x is. So shell is, you can say, rotating. So we have to find the total as well as the ratio. So we are going to start with our moment of inertia. So we know that moment of inertia of shell, that is I, is equal to 2 upon 3 mr square, and it is rolling without slipping. Rolling without slipping, therefore we can say that our omega is equal to V upon R. So we can find out the rotational kinetic energy. Rotational kinetic energy, let us call this as K rot, is equal to half I omega square. So this comes as our half 2 by 3 mr square, and this comes as V upon R whole square. So we get that K rotational will be equal to, this 2 goes by 2, R square is going to by R square. So we are left with this as 1 by 3, and we have mv square. And another energy that will be associated will be translational energy. So we can say translational kinetic energy, let us call this as K trans, will be equal to half m v square. Therefore total kinetic energy, let us put that is our K, will be equal to our rotational kinetic energy plus translational kinetic energy. So this comes as a 1 by 3 mv square plus 1 by 2 mv square. So we get our K is equal to, this will be a 6 and this will be 5 by 6 mv square. And we have to find out the ratio of our rotational to total. Therefore we can say the ratio will be equal to K rotational, K total, and rotational is our 1 by 3 mv square, and total is our 5 by 6 mv square. mv square cancels out, so this comes as 1 by 3 times, and 6 goes by 2, so we get this is equal to 2 by 5, and it is given as x upon 5. So this is our x upon 5. Therefore, value of x is equal to 2. X is 2. Next question. It states that a solid sphere is rolling on a horizontal plane without slipping if the ratio of angular momentum about the axis of rotation of the sphere to the total energy of the moving sphere is pi is to 22. Then the value of its angular speed will be. So ratio of angular momentum and the total energy of the sphere is given to us. Okay. Angular momentum is about the axis of rotation of the sphere. So let us start with it is rolling, so we can say that moment of inertia of sphere about the axis through its center. Which is a standard formula, that is I is equal to 2 upon 5 mr square, and its rotational kinetic energy let us call this as k rot, will be equal to half I omega square, and we also know that our v is equal to omega r because it is rolling without slipping. Therefore we can write that k rotational will be equal to our half, we substitute value of I is our 2 by 5 mr square, and omega is our v square upon r square. Here 2 r square cancels out, so this comes as our 1 by 5 mv square, and we have translational kinetic energy let us suppose this is k trans will be equal to half m v square. Therefore total kinetic energy that is our k will be equal to kinetic energy rotational plus kinetic energy translational. So we get this as k is equal to 1 by 5 mv square plus 1 by 2 mv square, and this comes as 7.10 mv square. We found out first part, that is our total energy. Now we have to find out the angular momentum. So we can say that angular momentum of the about the axis of rotation, angular momentum about axis of rotation, that is our L, will be equal to moment of inertia and angular velocity, that is omega, and this comes as 2 upon 5 mr square times omega, and we are supposed to find out their ratio because it is given as pi upon 22. Therefore we can say the ratio, that is our angular momentum divided by k total energy, which is our k. So angular momentum is our 2 by 5 mr square omega, and energy is our 7.10 mr square. Okay, so we can substitute this omega as v upon r. Okay, so let me substitute it here. This comes as v upon r, and this was either our 7.10 mv square. V square, and one second. Okay, so this r goes by r square, and we come this as our, let me keep this in omega only, otherwise it will be difficult to sort it out because it will be requiring more substitution. So we can write this as our 2 by 5, and we have this as mr square multiplied by omega, and this will be equal to our v is equal to omega r. So this will be equal to 7.10. V is omega r, so this r square and omega square. So this comes as 7.10 mr square omega square. Here mr square, omega, and this goes away. So this can be written as 2 upon 5 is equal to 10 upon 7 omega, and our 5 goes by this 10, so the ratio will be equal to 4 upon 7 omega, but this ratio is given as pi upon 22, and we have to find out, okay, we need to find out omega. So we can write that our omega will be equal to, this comes as our 4 upon 7, 22 upon pi, and pi is our 22 upon 7. So this 22, 7 and 7 cancels out, so we get that our omega is equal to 4. Value of angular velocity will be equal to 4. Next question. It states that a tight rope is wound around a hollow cylinder of mass 5 kg and radius 70 cm. The rope is pulled with a force of 52.5 Newton. The angular axis of the cylinder will be. Okay. So in this case, we can just draw an approximate figure. So we are having a hollow cylinder and a rope is wound on it. So let us suppose the rope is wound something like this, and this is the loose end of the rope, and here a force F is being applied, value is given to us, and because of that it is going to rotate. And suppose angular velocity is omega, angular acceleration is alpha, and let us suppose this is our center O and R is the radius. So this force will be, you can say, generating a torque on this cylinder. Therefore we can say that torque on the cylinder that is our tau will be equal to force multiplied by the radius, perpendicular distance, because it is going to rotate about point O. And we substitute the values, we get our torque is equal to 52.5 and radius is 70 centimeter, 0.7. This comes as our 36.75 Newton meter, and this torque will be generating an angular acceleration alpha. So we can say angular acceleration, that is alpha, will be equal to torque upon moment of inertia I, and I we can just, because it is a shell, so we can easily find out I, that is a moment of inertia. So we can say moment of inertia of hollow cylinder, which is our I, is equal to mr square. So we substitute the value, we get alpha is equal to torque upon mr square, and torque we found out is our 36.75, and mass is our 5, and this is 0.7 whole square. So this gives us that the angular acceleration alpha will be approximately equal to 15 radian per second. Per second square. Next question. States that a solid sphere and a solid cylinder of same mass and radius are rolling on a horizontal surface without slipping. The ratio of their radii of gyration respectively are 2 is to square root of x, then the value of x is. So this is directly based on the formula. We know the standard formula for radius of gyration, that is our radius of gyration, which is our k, it is given as square root of moment of inertia divided by mass m. And we have two different objects, so moment of inertia will be different. So we can say for sphere, this is solid sphere, let us call this as IS, will be equal to 2 by 5 mr square. So from here you can say our radius of gyration of a sphere will be equal to mass is m, and we put this as 2 by 5 mr square and its square root. So this m and m cancels out, and r we can just take outside the square root. So this comes as r as 2 upon 5. And next is our cylinder. So we can say for solid cylinder, let us call this as IC is equal to 1 by 2 mr square. Therefore, radius of gyration for the cylinder will be equal to, this is our I upon m, so this comes as m 1 by 2 mr square and its square root. This m and m cancels out, and this gives us radius of gyration for cylinder C will be equal to r square root of 1 by 2, and their ratio is said to be 2 square root. So we can say the ratio is our, for sphere cylinder will be equal to, this is r square root of 2 upon 5 r square root of 1 by 2. R and R cancel out, and this comes as our 2 upon 5 multiplied by 2 upon 1 and its square root, which gives us 4 upon 5 and its square root. We are given that the ratio is 4 upon 5 is equal to 2 square root of x, and this can be written as 2 square root of 5 is equal to 2 square root of x. Therefore, we get that the value of x will be equal to 5. Value of x is 5. So this completes all the 10 questions for the year 2023, and this was the only part 1 for 2023. Remaining questions we are going to deal with in part 2. Thank you.